Assuming you survived the gloom opening, you would arrive at one more. In the universe, there is currently an interrelationship between quantum processing and dark openings. In this educational video, we investigate a noteworthy and frightening discovery made by the James Webb Space Telescope inside a dark opening. Bill Nye, of course, provided an explanation. The science guy said a dark opening is a star so huge that even light can't escape it because of its enormous gravity. The secrets of dark openings have baffled researchers for many years. However, now, thanks to remarkable capabilities, we've witnessed something truly shocking. Something very large being consumed by a dark opening. Compared to one Earth every day, the staggering and compelling discovery, the very first picture of a dark opening in space, has changed our understanding. Prepare yourself as we dive into the unimaginable details of this cosmic discovery and its potential impact on our understanding of the universe. Stars toward the end of their lives, much greater and more massive than the sun, run out of fuel and begin to collapse as gravity crushes them. Dark openings are difficult to detect. It was a true challenge to find the first one. Despite the fact that Einstein's theory of relativity predicted they were common, similar to stars, dark openings do not produce any light themselves. Only their spin and size are measurable properties. Visual proof of dark openings confirming their existence has only recently become available. Conclusive evidence of dark openings was missing for a long time. The first was discovered in 1964, the dark opening Cygnus X1. Yet it took more than 30 years for specialists like Stephen Hawking and Kip Thorne to agree on whether Cygnus X1 was indeed a dark opening. Hawking, a prominent figure in dark opening research, believed in their existence but was cautious due to the lack of conclusive evidence. By 1975, when the bet was first cast, he and Thorne were nearly 100% sure that Cygnus X1 was a black hole. By 1988, 95% of scientists were convinced. Still, they waited until 1990 to accept the evidence, when more observations provided adequate confirmation. The initial discovery of Cygnus X1 was made using 2 Geiger counters launched into space on a suborbital rocket. They detected a signal pinpointed to a system 7,200 light-years away. The system featured a blue supergiant star orbiting another enormous object emitting strong X-rays, which made sense if the object was a dark opening. Much research has focused on Cygnus X1 since its discovery, revealing that it is 21 times the mass of the Sun, making it the largest stellar mass dark opening found without the use of gravitational waves. This revelation challenges long-held assumptions about dark opening formation and the mass loss experienced by stars over their lifetimes. Cygnus X1 breaks records in more ways than one, with its remarkable mass and the fastest rotation speed of any dark opening discovered so far, approaching the speed of light. These findings defy the accepted pattern of dark opening development. Although definitive proof of dark openings has only recently emerged, it is increasingly apparent that they are scattered throughout the universe. Even if researchers eventually uncover all the secrets of Cygnus X1, the first of its kind, countless others still hold surprises. Within 2,000 light-years from Earth, researchers have found a dormant behemoth. The Milky Way's largest stellar mass, dark opening, Gaia BH3, with a mass 33 times greater than that of our Sun. Despite being the second closest known dark opening to Earth, Gaia BH3 remained undetected until now. It was discovered accidentally while researchers from the European Space Agency were examining data from the Gaia mission, which maps our galaxy in 3D. The discovery of this dormant dark opening, which isn't actively pulling in material from a companion star, was a complete surprise. Normally, stellar mass dark openings in the Milky Way have masses around 10 times that of the Sun, with Cygnus X1 holding the record at 21 solar masses. But Gaia BH3, with 33 solar masses, still pales in comparison to the largest known dark openings. Take, for instance, the massive central dark opening in our galaxy, Sagittarius A, which is 4 million times more massive than the Sun. Gaia BH3 is the second closest known dark opening to Earth, behind only Gaia BH1, which is 1,500 light-years away, and has a mass multiple times that of the Sun. Cosmologists now have more evidence to understand how stellar mass dark openings form. These openings likely originate from massive stars with low concentrations of heavy metals. Such metal-poor stars, mainly composed of hydrogen and helium, are believed to lose mass more slowly, leaving more material available to form massive, dark openings when they die. Using the James Webb Space Telescope, JWST, specialists discovered an incredibly red, very massive dark opening existing in the shadowy early universe. As the universe expanded, this supermassive dark opening, existing around 700 million years after the Big Bang, took on a reddish hue. The red-shifted light suggests a dense layer of gas and dust surrounding the opening. Lucas P. Fennell and Aobi of the Bengal University of the NAS Cosmology Group calculated the dark opening's mass using JWST data, estimating it at about 40 million times the Sun's mass. This finding stands out from its surrounding universe, showing that this very massive dark opening is rapidly consuming nearby dust and gas. Situated about 12.9 billion light-years from Earth, this quasar was initially identified by its red appearance. Quasars form when immense material surrounds supermassive dark openings, creating a disk of gas and dust that feeds them. The gravitational pull disturbs the matter, producing extreme heat and making it shine brilliantly, often outshining all stars in their host galaxies. WST identified this very massive dark opening as a small point due to the enormous radiation it emitted. Initially thought to be a galaxy with unusual star formation based on color analysis, its small size and extremely massive nature stood out from other quasars in the early universe. This discovery was made possible by gravitational lensing, an effect Einstein predicted in 1915. His general theory of relativity suggests that massive objects warp the fabric of spacetime. This curvature creates gravity, and the more massive the object, the stronger the curvature. The curvature of spacetime also bends the light from stars as it passes near massive objects. This phenomenon, gravitational lensing, allows us to see distant objects that would otherwise be invisible. WST used this effect, aided by the SMACS J0723 galaxy cluster, to amplify the brightness of distant galaxies and reveal the red quasar. These new data contribute to the growing evidence that the early universe was filled with very massive dark openings, millions or even billions of times heavier than the Sun. Now that this phenomenon has been observed in many early universe supermassive dark openings, it sheds light on the development of both dark openings and the host galaxies, and the relationship between the two. The classic chicken or egg problem on a galactic scale remains unresolved. Did the galaxy form first, or the dark opening? How large were the first dark openings? How did they evolve? Researchers may have found evidence that microquasars, dark openings consuming massive stars, are cosmic particle accelerators, releasing unexplained high-energy astronomical beams that reach Earth. These massive dark openings pull material from nearby supermassive stars in binary systems, and some stellar matter is expelled as relativistic jets traveling at incredible speeds. Microquasars are smaller versions of quasars, both powered by supermassive dark openings consuming nearby matter. In 1912, high-energy particles began reaching Earth, particles with energies up to 1020 electron volts, far greater than anything, achieved by the Large Hadron Collider, the world's most powerful particle accelerator. The theory suggests these enormous dark openings and microquasars are the universe's most intense particle accelerators. However, until recently, evidence of microquasars accelerating particles to such extreme energies was scarce. Using the High-Energy Stereoscopic System, HESS, researchers identified extraordinarily high-energy gamma rays from the jets of the most powerful microquasar in the Milky Way, SS433. These gamma rays result from interactions between the jets and surrounding matter, creating shock fronts that accelerate electrons to extreme velocities. SS433, the first microquasar ever discovered, is located at the center of the W50 supernova remnant. Affectionately called the Humanity Cloud, there has been a lot of research done on SS433. Scientists have studied the system's components for many years. It consists of a white supergiant star and a dark opening 10 to 20 times larger than the Sun's mass. They orbit each other every 13 Earth days, with the outer layers of the star being snatched away by the dark opening's gravity. This results in the formation of an elemental accretion disk surrounding the dark opening, while other parts are ejected as jets traveling at 26% of the speed of light. These jets travel in a wavy spiral, transforming the W50 supernova remnant and making it appear to be a cosmic manatee. The jets fade over time, but reappear as a recurring phenomenon brought about by SS433's persistent activity. The jets from the dark opening also interact with the surrounding matter, creating a complex interaction between the gloomy origin and its environment. This behavior makes SS433 one of the most engaging and fascinating objects in the study of microquasars and their role in the cosmos. Despite SS433's particle acceleration being the first identified in a microquasar, many questions remain about how particles accelerate through dark openings to such extreme energies and their broader impact on the universe. Researchers use various methods, including indirect measures, to comprehend these cosmic entities. Dark openings, for example, can be monitored through their interactions with matter and nearby stars, as evidenced by the dramatic increase in X-ray emissions when material is pulled into their gravitational grip. This phenomenon is crucial for understanding dark openings and their influence on the universe, offering essential insights into the evolution and behavior of these enigmatic objects. In the realm of dark opening research, the recent discovery of the most distant known dark opening, an unprecedented 13.1 billion light-years away, has further expanded our understanding of these gigantic entities. This finding was made possible by the capabilities of the James Webb Space Telescope, JWST. JWST revealed a very massive dark opening formed less than 1 billion years after the Big Bang. This early formation challenges existing theories about dark opening development and galaxy formation. Observations suggest that these early dark openings may have played a significant role in shaping the structure of the universe by influencing the formation and development of the earliest galaxies. In addition to their role in galaxy formation, dark openings have been linked to a potent cosmic phenomenon referred to as active galactic nuclei, AGN. AGNs are characterized by extremely luminous emissions from the regions around supermassive dark openings at the centers of galaxies. This emission occurs when material from the accretion disk surrounding the dark opening is heated to high temperatures, releasing X-rays and other forms of radiation. Studying AGNs provides valuable insights into the feeding behavior of dark openings and their impact on their host galaxies. AGNs have been shown to significantly influence galaxy evolution by regulating star formation and dispersing heavy elements throughout the cosmos. Recent advancements in gravitational wave astronomy have provided a new way to probe the properties of dark openings. The detection of gravitational waves from merging dark openings by observatories such as LIGO, Laser Interferometer Gravitational Wave Observatory, Virgo, and others has opened a new frontier in our understanding of these elusive objects. Gravitational waves, ripples in spacetime caused by accelerating massive objects, allow researchers to measure the mass, spin, and other properties of dark openings that are otherwise difficult to observe. These observations have confirmed the existence of dark openings with masses ranging from a few to several solar masses, including the detection of mergers resulting in even more massive dark openings. Another intriguing component of dark opening research is their role in the production of high-energy cosmic rays and energetic particles traveling through space. These particles are thought to be accelerated by dark openings, especially those in microquasars or active galactic nuclei. The process involves interactions of relativistic jets with surrounding material, generating shock waves that accelerate particles to near-light speeds. Understanding the origins of these cosmic rays is crucial for deciphering their impact on the interstellar medium and the larger cosmic environment. In addition to their influence on cosmic rays, dark openings are also associated with the development of elaborate structures known as relativistic outflows. These are powerful jets of matter ejected from the regions around dark openings, moving nearly at the speed of light. The study of these outflows helps researchers comprehend the mechanisms behind the formation and evolution of supermassive dark openings and their impact on host galaxies. Observations of these jets have provided important data about magnetic fields and particle acceleration processes occurring near dark openings. Theoretical work has also explored the nature of primordial dark openings, thought to have formed shortly after the Big Bang. Unlike stellar mass or supermassive dark openings, primordial ones would have emerged from early fluctuations in the universe's density rather than from collapsing stars. If they exist, primordial dark openings could account for some of the dark matter in the universe. Identifying these elusive objects remains a significant challenge, but their study could yield new insights into the fundamental properties of both dark matter and the early universe. Dark opening thermodynamics and the study of Hawking radiation continue to be areas of active research. Proposed by Stephen Hawking, this hypothetical radiation suggests that dark openings could emit particles and gradually lose mass over time. While direct detection of Hawking radiation is currently beyond our technological capabilities, the concept has significant implications for our understanding of dark openings and their ultimate fate. Theoretical models and simulations help explore how this process could influence the lifespan and properties of dark openings. Another fascinating development is the investigation of the dark opening information paradox, a long-standing puzzle in theoretical physics. This paradox concerns whether information that falls into a dark opening is lost forever, or if it can be recovered in some form. Recent advances in quantum information theory and holography have led to new insights, suggesting that information might be preserved in a highly scrambled form and potentially recoverable. Finally, the detection of gravitational waves from dark opening mergers has not only confirmed the existence of these cosmic giants, but also provided a unique way to study their formation and evolution. These waves carry information about the masses, spins, and dynamics of dark openings, offering a powerful tool to investigate the fundamental characteristics of these enigmatic entities. Continued observation and investigation of gravitational waves will undoubtedly reveal much more about the nature of dark openings and their contribution to the universe. In summary, dark opening research continues to advance. With improvements in observational techniques, theoretical models, and new discoveries, from distant dark openings in the early universe to the complex interactions observed in microquasars, this remains a dynamic and captivating field with profound implications for our understanding of the cosmos.